morning. Happy coming New Year wishes to all. Before going to the lecture, let us pray for the COVID-19 affected persons to recover them soon. Also in this time, I would like to tell you all that we shall cooperate the government and we shall be at home and we shall safeguard our family, ourselves and the society. This lecture is the analytical discussion about the refrigerator driven by a heat engine. Before going to this, let us see how an heat engine works. See, this is the heat engine which receives the heat engine receives QS1 amount of heat from the source. Let us take T2, and after doing work W1, some part of heat is rejected out to the sink. Let us take the sink temperature as T1. The amount of heat rejected to the sink is QR1. Now let us find out what is the maximum efficiency. That is, the Carnot efficiency is the maximum efficiency, which is nothing but the high temperature. This one is the source is the high temperature and the sink is the low temperature. So Carnot efficiency for heat engine is TH minus TL divided by TH. Now let us take the heat engine operates between the temperature limits of 900 Kelvin. That is, source temperature is 900 Kelvin and the sink temperature, let us take it as 300 Kelvin. Let us substitute this value and find what is the maximum efficiency. So this is equal to 900 minus 300 divided by 900. So if you calculate the value, you get nearly about 0.66. So this is the maximum efficiency or Carnot efficiency of the heat engine. Also, we have efficiency is equal to output is work done by the engine W1 and the amount of heat supplied QS1. So this let us assume that the heat engine receives 1800 kilojoules of heat. Let us assume 1800 kilojoules of heat. Then W1 is equal to efficiency into QS1. So the maximum efficiency is, the Carnot efficiency is 0.66 multiplied by the heat supplied to the heat engine is 1800. So this is equal to W1. Work output we obtained from the heat engine. Now let us see what is the amount of heat rejected to the sink at 300 Kelvin. Before that, let us calculate this value and let us find out what is the value of W. So it comes around 1200 kilojoules. Now let us find out what is the value of QR. Heat rejected to the sink. This is equal to heat supplied to the heat engine minus work output from the heat engine. QS1 minus W1. So this is equal to 1800 kilojoules minus 1200 kilojoules. So this is equal to 600 kilojoules. So this is the amount of heat energy rejected to the sink. Let us take this as QR1, QR1. So the heat energy rejected to the sink is equal to 600 kilojoules. The work we obtained from the heat engine is 1200 kilojoules. The maximum efficiency of that is the Carnot efficiency of the heat engine is 0.66. Now let us discuss about the refrigerator. So this is the refrigerator in which work is supplied. It extracts heat from the low temperature body. So this is TL and it rejects to the high temperature body. Let us take it as TH. Let this temperature be, low temperature be T2. And let us take this as T1. Let us assume that refrigerator operates between the temperature limits of 250 Kelvin and 300 Kelvin. Let us take the work input to the refrigerator as W2. So heat engine is a work delivering equipment, whereas refrigerator is a work consuming equipment. So for this, here we are saying the efficiency as Carnot efficiency in terms of Carnot efficiency. Here what we are saying is Carnot COP, coefficient of performance. So when it operates between the two temperature limits, the COP is given by low temperature to the difference in temperature, TH minus TL. Let us find out what is the maximum COP of the refrigerator. So this is equal to 250 divided by, this is TL is 250, TH is 300 minus TL is 250. So this is 50, 250 divided by 50, this is equal to 5. So the coefficient of performance, maximum coefficient of performance of this refrigerator is 5. So this is the heat extracted from the low temperature region. Let it be QS2 and QR2 be the heat rejected to the high temperature body. So from these temperature limits, we have calculated the COP. Also, COP is equal to refrigerating effect by work done. So amount of heat rejected, QR2 divided by work input. This is not work done, work supplied to the system, W2. So from this equation, now let us assume a work of 840 kilojoules is supplied to the refrigerator. So amount of heat rejected can be calculated W2 into COP. So W2 is 840 multiplied by COP 5, we get QR2, amount of heat rejected, as 4200 kilojoules. Now let us find out what is the heat supplied. Now let us find out what is the heat extracted from the low temperature body. We have W2 is equal to difference in temperature, QS2 minus QR2. So from this, QS2 is equal to W plus QR2. So this is equal to 840 plus QR2 is 4200 kilojoules. So this is equal to 840 plus 4200, 5040. This is QS2, that is the quantity of heat extracted from this refrigerator when it is operated between the temperature limits of 250 Kelvin and 300 Kelvin. Now I am combining these two things, that is heat engine and refrigerator. Now the refrigerator is driven by the heat engine, which are at these conditions. Let us assume that the heat engine operates between these two temperature limits, 900 Kelvin and 300 Kelvin. Similarly, let the refrigerator operates between these two temperature limits, 250 and 300 Kelvin. Now the combined system schematic is like this: 900 Kelvin, this is QS1, this is PH1, this is heat engine, work output W1, heat rejected to the sink QR1, this is sink which is at the same temperature 300 Kelvin. This is TL. So we have maximum efficiency as 0.66, heat supplied to the engine QS1 is equal to 1800 kilojoules, QR1 is equal to 600 kilojoules, and W1 is equal to 1200 kilojoules. This is refrigerator, which is extracting heat from the low temperature region at 250 degree Kelvin, and This is work consuming device. We take this as W2. So W2 is equal to 840 kilojoules and W1 is 1200 kilojoules. So there must be some net work output from the system. So this is equal to 1200 minus 850. So net output from the combined system is W is equal to W1 minus W2, which is equal to 1200 minus 840, which is equal to 360 kilojoules. So the net work output from the combined system is 360 kilojoules. So here QS2, this is QR2. So this is the combined system. So here the maximum COP is of the system is 5. Heat extracted from the low temperature body QS2 is equal to 50-40 kilojoules and QR2 is equal to 4200 kilojoules. So this is QS2 is equal to 50-40, QR2 is equal to 4200 kilojoules and COP is work input to the system. You have already assumed that it is 840 kilojoules. So this work is obtained from the heat engine. 1200 kilojoules of heat is obtained from the heat engine. From this 1200 kilojoules of heat, 840 kilojoules of heat is supplied to the refrigerator, and the remaining work, that is the net work output from the combined system. So this type of system, suppose if you are running the refrigerator by these parameter values of heat engine, we get a COP of 5 and the amount of heat extracted from the low temperature body is 50-40 kilojoules and the heat rejected to the sink body is 4200 kilojoules. So this is the combined heat engine and refrigerator system. So this is the otherwise I can call it as a refrigerating system run by a heat engine. Any clarifications in this, you can call me at any time, and your suggestion and comments are welcome. Thank you very much. Thank you.